right, hello students. So today we are doing day 5 for our nuclear chemistry notes. So to get started, chemical reactions. So chemical reactions are something that happen between electrons of different elements. So it happens between electrons of different atoms. So it's two separate atoms reacting together, whereas a nuclear reaction is in the nucleus of an atom. So we're going to say in the nucleus of an individual atom. So when we talk about nuclear chemistry, we are talking about reactions that are happening inside of one atom. It's not between two different ones, it's inside of one singular atom. So, radiation. Radiation is the term for energy emitted from radioactive substances. So some atoms are unstable and radioactive. Radioactivity, the spontaneous emission of radiation from the nucleus of an atom in order to increase its stability. So we can have some atoms that are not stable in the form that they are in. And so they go through radioactivity, they emit radiation to increase its stability so that it can just chill, right? It doesn't want to be all over the place. It doesn't want to be unstable. So it's going to emit radiation in order to increase the stability. And then there are 3 types of radiation. There are alpha particles, beta particles, and gamma rays. So we will be discussing all 3 types of radiation today, and they all have different strengths. So let's go to alpha particles. Alpha particles are particles that have a mass of 4 and a charge of positive 2. So think of it like helium. That's what we'll see down here. Penetrating ability, that's low. So when we talk about penetrating ability, all it means is what can it go through, what can it penetrate. So alpha particles are actually blocked by a piece of paper. Their penetrating ability is so low that they can't pass through a piece of paper. The symbol is alpha, so it's this little A, weird A thing. And the isotopic notation that we'll use in examples and chemical reactions is just the helium notation. Mass of 4, charge of positive 2, so that's helium. Alright, so let's look at some examples. Okay, so here you see a little box. It's supposed to be an arrow. So if you want, you can just draw a little arrow over it, pretend that was there to begin with. But, so we're starting with uranium. Yay, uranium, right? So, uranium is what we call the parent nucleus. So it's what we're starting with. And then once it goes through its alpha decay, we're going to end up with our alpha particle, right, that helium that we talked about, and then a daughter nucleus. So it's what's produced. And this, a lot of times, you'll have to figure out. You won't always be given it. So let me show you how you can figure that out. So first step we have to do is look at our parent nucleus. So if you see, it's uranium. It has a mass of 238 and 92 protons. So that is what you will see on your periodic table. So now, when it goes through its decay, we end up with a helium, and we're going to end up with another atom. Okay, but oftentimes we'll have to figure out what this is. So we're going to use the two things that we're given to find what we need, kind of like math. So we have 238 over here and 4 over here. So I'm going to think of this as X. So I'm sure you've seen this when we were going through the notes a couple days ago. So I like to think of our daughter nucleus as an X, 3 different X's. And we're just going to plug in the X for what we're looking for math, right? So we have 238, so we're going to do 238 and then 4 over here, right? So we're going to pretend this is an equal sign, equals 4 plus X. And what do we do in math to find X? We get it by itself, right? So we're going to subtract. So our X is going to be 234. Awesome. So we found that, right? 234. All right, now let's find our protons. So we're starting with 92. We have 2 over here, so let's write our equation again. Equals 2 plus X, right? Because there's a plus here. And we get X by itself, so we subtract 2. So our X is 90. Perfect. So now what we're going to do is look on our periodic table. And when you look on your periodic table and find your atomic number of 90, then we end up with thorium, which is TH. So now we can cross that out, and look at that. We have our missing atom in the correct notation. Alright, so let's try and practice this on your own, right? So whenever you see this little box, we're just going to draw an arrow. I don't know why it didn't print out like it was supposed to, but it didn't. So here's an arrow. Alright, so we're looking at alpha decay, right? What does alpha decay mean? What are we going to have right here? Well, we're going to have this helium, right? This helium notation. That's what we use for an alpha particle. So we're going to write that first off. Helium, and then 2 and 4. Awesome. So now we're going to go through our little math to find what we're missing here, right? So I'm going to give you a second to do that. Alright, so we're going to pretend it's X, right? So we have 226 equals, right, because of that arrow, 4 plus X. So minus 4, X is 222. Alright, so that's our mass, right? So now let's find our atomic number. Same way. 88 equals 2 plus X minus 2, X equals 86. Awesome. So now we have what we need to figure out what our element is, right? So we'll go back to our periodic table. 86 is radon. So we're going to put R in, and then 86 and 222. Great job. Loving it. All right. So now let's go to our next page. We're going to learn about beta particles now. So, beta particles have a mass of 0 and a charge of -1. Well, so what has a mass of 0 and a charge of -1? It's an electron, right? So down here on our isotropic notation, we're going to put our isotopic notation for an electron. Alright, so if alpha particles had a really low penetrating ability, beta particles have about a medium penetrability. So we're just going to put medium. And when we say medium, it means it can be blocked by a piece of aluminum. So it's a little more hefty-duty than a piece of paper, but a single sheet of aluminum will block the beta particles from going through. All right, so now let's look at our example. We're starting with silver, and a little box, right? We draw our arrow, and we end up with our beta particles and another atom, right? So Cd, that's cadmium. So let's figure out how we got this, right? Because you're going to be given this and this most of the time, and you're going to have to find what we're missing here. So it is the exact same idea as the alpha particles, right? So you're given numbers here, and you're going to use them to find the numbers here. So we're starting with 111 equals 0 plus x. Well, then what does that mean x is, right? X is still just 111. So the mass, when we're dealing with beta decay, doesn't change. But because we have an electron, our atomic number will. So do the same thing. 47 equals -1. You cannot forget that negative. It makes a big difference. It is -1 plus x. And it makes a big difference because now, instead of subtracting like we did on the alpha decay, we're going to add it, right? Because it's negative. Meaning our atomic number is now 48. Not 46. It is 48 because we had to add that number. We had to add that 1. So look, that's what we got here, what we got here. Perfect. So now 48, we will look at our periodic table, which is Cd, right? Cadmium, which we already knew because it was right there, but we're going to pretend like we didn't, right? So now we know that our atomic number is 48, our mass is 111, and our element is cadmium. And look at that. Great job. So, your turn. So let's start with the beta decay. I draw our little arrow. For some reason it didn't show up. Okay. Okay, so beta decay, right? What do we use to notate beta decay? The electron, right? So first thing we're going to do is write that. -1. -1, -1, -1. Not positive. It is -1. Alright. So now we're going to find what we're missing, right? Do exactly as we did before. I'll give you a second. Alright. So 90 equals 0, and then plus our x, right? So that means our x is just 90. Easy peasy. Doesn't change. Alright, so now I'm going to put 90 up here. Alright, so now let's look at atomic number. 38 equals -1 plus x, right? We're going to add it to both sides. So x equals 39. 39. So now we're going to look at our periodic table and find 39. So 39, I always have a hard time pronouncing this. It's a Y. I can't pronounce it to save my life, but it's on the periodic table, it's number 39, and it's going to have a mass of 90. All right, fantastic job. Y'all are rocking it. So, now gamma rays. I always like gamma rays. I think they're a bit easy, and also it makes me think of the Avengers and Incredible Hulk. I'm a big superhero fan, so I'm always particular to the gamma rays. But gamma rays are high energy. High energy. Oh, sorry, I forgot a word. High energy radiation. So when they emit radiation, right, it's really high in energy. It's got a mass of 0, as well as a charge of 0. Mass is 0, charge is 0. Super easy, like I said, right? Well, since our energy is super high with gamma rays, our penetrating ability is really high. What blocks a gamma ray is lead or thick concrete. So it's blocked by lead or thick concrete. It takes a lot to block these gamma rays. Alright, this symbol is gamma. It's this little weird thing here. It's kind of how I draw it. And then 0 for 0 mass, and 0 for 0 charge. And that's how you'll see it in any formula. Alright, any reaction. So, fantastic. We're not going to do any examples for gamma ray decay because, I mean, it's 0, 0, and we're just not really going to see them. So, we're going to move on to our table comparing the 3 types of nuclear radiation. So, composition, alpha. Composition means that's isotopic notation. So, He, 2, 4. Alright, beta. That's our electron. And then gamma. So gamma is made up of EMR. So that's what we're going to write here. Okay, so EMR is electromagnetic radiation, right? So that's what we think of when we think of the microwaves, the gamma rays, gamma waves, visible light, but you'll learn about that a bit later. So, symbol, our symbol, right, for alpha is that A. That weird looking A. Beta is a B. It's got a little curve at the bottom. I always like drawing that one. And then gamma is that weird thing. I drew it a little iffy, but I mean, that's gamma. Alright, so mass. Remember, we can look at that from our notation. Which one of those is mass? It's the 4, right? Fantastic. So, alpha particles have a mass of 4. Beta particles, well, they have a mass of 0. And gamma rays, also mass of 0. Alright, so the electric charge is given to you, right? So electric charge was 2. Beta was -1. And gamma is 0. Awesome. So let's talk about our penetrating power. What was the penetrating power of our alpha rays, alpha particles? Low, right? It was low. I always like to think of these in alphabetical order. So alpha comes before A, comes before B, comes before G. So A is stopped earlier than B is stopped, earlier than G is stopped, right? So alpha goes penetrates the least, beta penetrates the middle, and then gamma penetrates the farthest. So you can use alphabetical order to help you remember that. Alpha A comes first, so alpha is stopped first. G comes last, so gamma is stopped last. Alright, so then beta, right, that has a penetrating power of medium. And gamma, as we said, it has a high penetrating power. Alright, shielding needed, so that means what is it blocked by? So alpha rays, alpha particles, right? What were alpha particles blocked by? Paper, right? So we can just use paper. We can use a piece of cloth. You know, really thin things like that will stop alpha particles in their tracks. Okay, beta. So what blocked those beta particles? Aluminum. Fantastic. Yes, aluminum blocked those beta particles. And gamma, right? That was the lead or the thick concrete, right? Require a lot of thickness and power to stop those gamma rays. Kind of like it takes a lot of power to stop that Hulk, right? So, last thing we're going to talk about is actually fission and fusion. Now, they're not on your notes, but we do need to talk about them real quick. So, when you go to the next page, you're going to see alpha radiation, right? So this is some practice for you. So I want you to just flip to that blank page. And we are going, here's where you can take notes about fission and fusion. So, fission happens when one atom splits into two atoms. Alright? So it's when we have one particle, one atom to begin with, and we end up with two. So a reaction you might see will often be with uranium. So we'll have uranium-235 and 92, right? So we'll draw our arrow, and it's going to be split into xenon and strontium. Now, for fission and fusion, you won't have to worry about figuring out what it splits up into. For your quiz, for your test, you will just have to be able to identify that this is fission. Fission, right? So fission, there's like a fissure in the concrete, in the sidewalk you're walking on. It's split up into two pieces. Whereas fusion is as its name suggests. Instead of one atom splitting into two, we're going to have two atoms forming into one atom. So we could have hydrogen, the mass of 2 and a charge of 1, and then another hydrogen, but this time with a mass of 3 and a charge of 1. Well, when they come together, they're going to form helium, charge of 2, and a mass of 4. So, if you think about it, fusion, right? Fusing together, coming together, 2 going into 1. Fission, fissure, breaking apart, 1 going into 2. Awesome. Great job today. If you have questions, please feel free to ask your teacher. Come to any chemistry teacher's tutorials. We would love to help you. So I hope that this was helpful, and you have a great rest of your day.